So now we're up to the second translation theorem. And it says that if we have the Laplace of f of t, and that's capital F of s, and if a is greater than 0, then if we want to take the Laplace of f of t minus a times that unit step of t minus a, then it's going to be e to the negative as times our f of s, which was the Laplace of f of t. So think about what that's saying. I want to go through and actually want to prove that so you can kind of see where that's coming from. So that's what the translation theorem is saying. And we just need to recall what that unit step's saying. Remember that unit step takes on the value of 0 when t is between 0 and a. And then it takes the value of 1 when t is greater than or equal to a. So let's start the proof. We want to prove the Laplace of that. So to find the Laplace, let's recall that also. The Laplace of f of t is equal to the integral from 0 to infinity, e to the negative st f of t dt. So we're going to apply that definition here. But remember, u of t is actually a piecewise function, so we have to split this into two pieces. One piece going from 0 to a, and then the other piece going from 1 to infinity, or a to infinity. So it's going to be e to the negative st times f of t minus a times the value for that unit step at t minus a. Now keep in mind this guy's going to take a value at 0 when we are between t and a. So we'll write that out in just a minute. And then that second piece, negative st f of t minus a, unit step t minus a dt. And this is going to take on the value of 1 since we're between a and infinity. So t is greater than or equal to a. So let's write this out. We have e to the negative st, f of t minus a. This guy's going to be 0. This guy's going to be 1. We know 0 times anything is 0. So that's gone. So we really just need to integrate this. Let's do a u substitution now. So let's let u equal t minus a. So if we were to do that, then t is equal to u plus a. And then if we take the derivative of u, then we would get dt. And let's look at bounds. If we look at our lower bound, remember this is in the world of t. So when t is equal to a, u is equal to a minus a, which would be 0. The upper bound, t is going to infinity, so t is infinity. And if we plug infinity in here, infinity minus a would just be infinity. So we're completely translating this into this world of u. So then when we do that, our lower bound is 0 and the upper bound is infinity. So we have e to the negative st But remember, t is u plus a. T minus a we called u. So I'm going to do a rewrite here on that exponential piece. This is e to the negative su, e to the negative sa, f of u du. Now, this guy's just a constant, so let's pull it outside. So if we look at this guy, let's go back to that definition of the Laplace up here. It's from 0 to infinity, e to the negative st, f of t dt. So if we use a different variable like u, this is still going to be the Laplace. So it's the Laplace of our f of u. So by definition, that's what that is. And if we find the Laplace of f of u, it's just going to be some function in terms of s. So there's our proof of that second translation theorem. If we were to take the Laplace of this guy, it does end up being this. So we do have to be careful because there is a little thing that happens here. We do have to make sure that whatever this is has to be the same inside of the unit step and inside of the parentheses here, that f of t minus a has to be the same. So that's the big catch. So now let's look at a few examples. Let's say we want to take the Laplace of this guy. So we could take the Laplace of each piece separately. So in the Laplace of 1, we already know what that is. Going back to that table, it's going to be 1 over s. The question is, what's the Laplace of this and this? Well, we really need to derive something. So let's do that off to the side. Let's say we want to find the Laplace of the unit step of t minus a. So remember, that means that if we were to integrate from 0 to infinity, using that definition for Laplace, and once we do it once, we can use it every time. We would have that. So remember, this takes on the value of either 0 or 1, so I'm going to rewrite that this way. We are going to have to split this into 2 pieces. So we're going to have e to the negative st times that unit step, t minus a dt. But this guy's going to take the value of 0 as long as we're between 0 and a, which means that's going to be 0. And then here we're going to have e to the negative st times the unit step of t minus a dt. But this is going to take on the value of 1 as long as t is greater than or equal to a. So then we really end up just integrating from a to infinity, e to the negative st dt. So then to do that, we could think about u substitution. We would need a negative s here, compensate with a negative 1 over s here. And then when we integrate, e to the u is going to be e to the u, going from a to infinity. We could use limit notation here. I'm going to skip the limit notation. I'm going to rewrite it this way. So we have negative 1 over e to the infinity. Which means this guy's just going to get smaller and smaller and smaller. And that second one is going to kind of be stationary there. So this guy's heading to 0. So we've got 1 over s e to the as. And we can rewrite that as e to the negative as over s. So then we just showed the Laplace of the unit step of t minus a is equal to e to the negative as over s. And if we look on our Laplace tables, we're going to see that's our number 51 there. So you can see where that guy's coming from. So we found the Laplace of the first piece. Now let's do the second and the third pieces. If we apply this to this, we're going to have e to the negative 2s over s. And then that last piece is going to be e to the negative 3s over s. So all of these already have a common denominator. So we could just rewrite this as 2 minus 3e to the negative 2s plus e to the negative 3s all over s. Or we could leave it like that. Either one would be perfectly fine. So I want to do a couple more of those, finding the Laplace of a function that's written in terms of the unit step function. We actually solved these two problems. I don't remember if it was this video or the previous video, but we took this and we wrote it in terms of the unit step function. So just to kind of recap that, this function, if we were to graph it, I'm going to draw it over here, starts at 2. And then is 2 up to 3. And then once we hit 3, it jumps down to negative 2. So it starts at 2. And then it's going to jump down 4 units. So that's where that minus 4 is coming from. If I were to turn this on at 3, remember this guy's going to take on a value of 1. So then I'm going to have 2 minus 4, which is going to give me that negative 2 that I need here for that output. To recap what this one's doing, this is the 0 function up to 1, and then it turns quadratic at 1. We're looking at that piece of t squared, which would be this piece. So between 0 and 1, this guy takes on a value of 0. So t squared times 0 would be 0. But as soon as we hit 1, it flips the switch, and it turns this guy on. So I have t squared times 1, which is going to be t squared. Now, let's talk about taking the Laplace of these. So if I want to take the Laplace of this guy, so we're going to have the Laplace of 2, or we could write that 2 Laplace of 1. Minus 4 Laplace of the unit step t minus 3. So the Laplace of f is just that capital F of s. The Laplace of 1 is 1 over s. And then this guy was using that formula that we derived just a few minutes ago. And it gives us e to the negative as over s. So in this case, our a is 3. So I'm going to clean that up. We have 2 minus 4 e to the negative 3s all over s. So that second one is going to be a little bit trickier. So we want to take the Laplace of t squared unit step t minus 1. Now we have to be careful here, because we have a function times the unit step of t minus 1. We don't have a t minus 1 here. Otherwise, this would be easy. It would be that second translation theorem, but it's going to have to be tweaked a little bit. So if we go back to our sheet, we do have a formula for that. And look at number 53. So it's some function g of t times a unit step. So if we were to do that, we have to do a replacement in that function here, and we need to replace that t with a t plus a. So we're going to take the Laplace. So it's e to the negative as times the Laplace of g of t plus a. So it's going to be e to the negative, our a is 1s times the Laplace of, and we're using a function f of t, so I'm just going to use f of t plus our a. So if I were to take this and replace that t, I'm looking at t plus 1 squared. And if I were to multiply that out, t squared plus 2t plus 1. So remember, we're going to have to take the Laplace of each piece separately. And then we're going to end up multiplying by e to the negative s. So the Laplace of t squared plus 2 Laplace of t plus Laplace of 1. I don't know about you guys, but I think it's fun to write that funny looking L. It's kind of cool. So t squared, going back to our formula, that's going to be 2 factorial over s cubed. Laplace of t is 1 over s squared. Both of those formulas are coming straight from our sheet. T is 1 over s squared. T squared would be 2 factorial over s cubed. And then 1 is 1 over s. So I'm just going to write this just a little bit neater. We have e to the negative s, and that's multiplied by 2 over s cubed plus 2 over s squared plus 1 over s. So there's our Laplace. There's our final answer. So we can talk about where that formula came from the chart that we had to use in the last problem. And it's really an alternative form of the second translation theorem. So I want to go through and I want to prove this so you can see where it's coming from and see that we're not just pulling it out of our hat here. So our goal is to prove this. So just to kind of recall a few things we're going to need for this proof. The unit step function takes on the value of 0 as long as t is between 0 and a, and then 1 if t is greater than or equal to a. So that's our unit step. And then we also need to recall that if we take the Laplace of f of t, by definition, it's integrating from 0 to infinity, e to the negative st f of t dt. So let's take the Laplace of g of t, unit step, t minus a. We know we're going to have to split this into pieces because of that unit step. So we're going to go from 0 to a, and then we're going to go from a to infinity. So applying that Laplace here, it's going to be e to the negative s of t, g of t times that unit step. But in this case, that unit step is going to take a value of 0 because we're between 0 and a. And then here, this guy's going to take a value of 1 because we're from t to infinity, so we are beyond that a value. So 0, when we integrate and we find that definite interval, that's just going to be 0. So we're left with this guy. And we're going to end up having to do a u substitution again. Remember, this guy's just going to be 1, so 1 times this piece is that piece. So let's do a u substitution. Let's let u equal t minus a again. So then du would be dt, and then t is going to equal u plus a. Let's talk about bounds. For the lower bound, in the world of t, we're at a. If we were to change to u, then we're going to have a minus a, which is going to be 0. In the world of t, we're going to infinity. If we replace that t with infinity, infinity minus a number is still going to be infinity. So here's what we have. We are now integrating from 0 to infinity, e to the negative st, but t is u plus a. We're replacing this t also. So we have the same thing here and here, which means this guy is going to be the Laplace of g of u plus a. Alright, let me back up a minute. Let's erase that. So, we've done this u substitution. We're down here. Now, just like when we proved that second translation theorem a minute ago, we're going to still rewrite this guy. Our goal is to try to get this to look like that definition for Laplace. That's our goal. So let's rewrite this. So now we have that. Now this guy, just like before, is a constant, so we can pull that constant out. And we're integrating from 0 to infinity, e to the negative su times this function. So thinking back to our definition of Laplace, I'm going to shrink this down so we can go back to it. That was one of our things we needed. There's our definition of Laplace. So, and notice it matches this guy. So then, That's just the Laplace of that function, g of u plus a du. So, there's our proof of the alternate form of the second translation theorem. And that is on our cheat sheet. I believe we said it was 53. Yeah, so there's 53. There's our second translation theorem. This guy was our first translation theorem, number 52. And then 51, u of t minus a. That was what we derived a little bit ago to help us solve one of the problems. So you can see where all those pieces are coming from.